So we've seen how to compute the surface area of parameterized surfaces, but if our surface is instead given to us implicitly, so the set of all x, y, z such that f of x, y, z is equal to c, how can we compute the surface area of a surface given to us like this, since parameterization is not always easy to find? So the rough idea is that we'll compute the area of S by looking at the area of its projection or shadow onto some plane P. So we'll let P be a unit vector normal to a plane P, and we'll usually take P to just be K, so that P is the XY plane, or maybe I should say parallel to the XY plane, but it doesn't really matter. But sometimes it's also useful to take, you could also take P equals J or I, depending on the situation. So what we'll need, crucially, is that the gradient of f of x, y, at x, y, z is not orthogonal to P for all, I should say, for all f, x, y, z equals C. So for all x, y, z in our surface P. And this is to guarantee that if this were our surface, if the surface were to fold back on itself, then we'd sort of have two things above like the same point down here, and then we wouldn't be able to correctly count the surface area. So this is why we might want to take other choices of P in case we need to sort of project onto a different plane, like this. So for example, if our surface was the unit sphere x squared plus y squared plus z squared is 1, then there is no possible choice of P for which this will work, because if this is our plane, then we'll have 2 points above the same thing here. If we took a different plane like this, we'd still have 2 points above the same thing here. So to calculate the surface area of a sphere by the method we're about to show, we would have to calculate the area of a hemisphere and then double that. 2 times the area of this. Okay, so that's sort of the intuition. So we'll let P equals K. Again, this can work for any unit vector. It'll just sort of simplify the exposition to take this case. And suppose that the gradient of f dot P, which is, so yeah, suppose gradient of f dot P is never 0 at points of S. So meaning points where f of x, y, z is equal to C. So in our case, this means that, so del f dot K is not equal to 0. And that is the partial of f with respect to z. So we're assuming that the partial of f with respect to z never vanishes on our surface. So this implies, so the implicit function theorem, which I don't think we really discussed in much detail, but is somewhere in chapter 14, implies that in this case, So this will guarantee that the surface S never folds on itself, which means that it will pass the vertical line test. So this implies that S is the graph of a function. So S is Z equals H X Y. Started drawing F, but I meant to draw an H. So Z is the graph of a function for some function H, but we usually don't know. We don't have an explicit, we don't have a formula for H, we just sort of know that it exists. Okay, so let's start with this and then try to figure out how we can get enough information out of H to do what we want. So under this condition, we take R of xy equals xi plus yj plus h of xyk. So this will give a parametric description of S. So we can find the surface area by integrating. So if we take Rx cross Ry, this will be a determinant I, jk, 1, 0, h sub x, and 0, 1, h sub y. Which is, let's see, so this will be negative hxi with j, then we'll have, so this is, okay, so minus hyj, and then plus k. So the magnitude of Rx cross Ry is root 1 plus hx squared plus hy squared. Well, so far this isn't all that helpful since we don't know what hx, we don't know what h is, so how can we figure out what hx and hy are? Well, we can do this using implicit differentiation. So implicit differentiation gives that del h by del x is negative fx over fz, and del h by del y is negative fy by over fz. So as a reminder, how we derive this formula, these formulas, is to say, okay, so f of r xy by assumption is equal to c. So if we differentiate both sides, we get 0, since the derivative of a constant is 0. Then the chain rule tells us that the derivative, so if we do partial by partial x of this, the chain rule will tell us that partial d by dx of this is fx plus fz hx. And so then then we rearrange to get that hx is, so this comes over here, negative fx, and then we divide by fz. Okay, so this is that's how you derive these formulas. And so having these, we get, okay, so this is root 1 plus fx squared over fz squared plus fy squared over fz squared. We can bring all of that over. So we can bring that as fz squared plus all of this over fz squared. And this is a square root. So this will become 1 over fz. Maybe I should put absolute values around this. Root fz squared plus fx squared plus fy squared. But root fx squared plus fy squared plus fz squared, this is exactly the magnitude of the gradient of f. And similarly, the magnitude of fz, this is magnitude of gradient of f dot k. And in general, we could put del f dot p here for sort of using a general unit vector p instead. So our formula for the magnitude of this cross product, we can simplify to, write it up here, Rx cross Ry magnitude is nabla f over magnitude of nabla f over magnitude of, over absolute value of del f dot k. So the surface area of an implicit surface is given by A equals integral over region R of magnitude gradient of f over absolute value del f dot p, where del f dot p is not equal to 0. So let's take a particular example of this. In particular, if we have, so the surface area of a graph z equals fxy is given by the integral over R. So this is where, so if we're graphing it over some region R in R2, this will be given by the integral of root 1 plus fx squared plus fy squared dx dy. This is sort of, I guess we kind of derive this formula implicitly in the just preceding derivation, but one way to remember it from what we just did is to say, well, we define f of xyz is f of xy minus z, then del f, magnitude del f is root 1 plus fx squared plus fy squared, and del f dot k is 1.